In organic chemistry, we say that there are generally 4 types of intermediates: carbocations, carbanions, carbenes, and radicals. And we've not said much about radicals up to this point, except that they're carbon centers that have an unpaired electron. And so we can draw a radical like this. A free radical is an intermediate that is electron deficient, but unlike the carbocation, it's overall neutral. We generally say that the carbon is sp2 hybridized and has a trigonal planar geometry, although in some cases it's more like a very shallow trigonal pyramid. The unpaired electron sits in an atomic p orbital perpendicular to the trigonal plane. Now, like most carbocations, the radical can be stabilized by alkyl groups, and so we can see this in the diagram on the right. And so let's say we have a radical that looks like this. We have a hydrogen here, Our radical, our unpaired electron is sitting perpendicular to this plane here. But let's say we have a methyl group on the right-hand side instead of just a hydrogen atom. And we know that in carbocations, sigma donation can occur. Well, the same thing can happen in radical species. And so we can take this sigma CH orbital and overlap it with the singly occupied atomic p orbital bearing that radical. And so we see that there's a sigma CH overlapping with an atomic p orbital on carbon, and this is going to stabilize the overall radical more than having an unsubstituted one. And so what we can say is then that tertiary radicals are more stable than secondary radicals, which are much more stable than primary radicals. Similarly, benzylic and allylic radicals can be stabilized by resonance. Okay, so either sigma donation or resonance are going to stabilize these systems. And so the example of resonance is here. And so if we can take this radical and draw a set of arrows with singly headed arrows to give us a new radical in which that unpaired electron has moved over to the left-hand side. All right, and so this is an example where this particular radical is highly stabilized across the pi system. So why would radicals be stabilized by these effects? Well, in the case of the resonance form, you can place that unpaired electron on multiple atoms, and so this is going to be incredibly stable. But what about the system where we have a sigma donation? Let's look at the molecular orbital diagram for a free radical intermediate that undergoes sigma donation. And so we're going to draw out this system exactly as we've drawn it before. Okay, so we have now a radical here. We've got this atomic p orbital that has that unpaired electron in it, and we've got this methyl group on the right-hand side. And so this methyl group, we said, is undergoing that sigma donation. And so we have a sigma CH bond overlapping with an atomic p orbital on carbon. Now that happens, but what can we say is driving the stabilization here? Well, if we take a look at the way that these two orbitals are interacting. So let's say we have two electrons from the sigma CH overlapping with an atomic p orbital on carbon that has only one electron in it, and those two orbitals mix. What can happen is you can get one new orbital, the new sigma CH, goes down in energy, whereas the atomic p orbital on carbon goes up in energy. And so the net effect is that now you have stabilized the electrons as a whole. You stabilize that lowest energy orbital, that sigma CH, and so in the bonding orbital, you're going to get a lower energy intermediate. Okay? So before we talk about the reactivity of radicals, we first need to understand how radicals are formed in the first place. And so recall that according to molecular orbital theory, a sigma bond is formed from the overlap of two electrons, where one electron comes from one atom and one electron comes from another atom. So it might seem possible then that you could break a sigma bond homolytically to generate two radicals. And that's exactly what happens. So homolytic bond cleavage is where a sigma bond is broken equally. So that each atom receives one electron from that sigma bond. And in the process, right, thus forming two new radicals. Okay, so we use singly headed curly arrows to describe this type of cleavage. And the energy required to break a bond homolytically is called bond dissociation energy. And so this is the energy that's required to break this bond homolytically. This is otherwise known as the BDE. Right, energy required to break bond. And these BDEs are usually a little bit lower than the heterolytic bond cleavage, in which you've got two species that are charged. One is negative and one is positive. And so the reason why these BDEs are a little bit lower than homolytic bond cleavage is because that no charges are generated. Okay, and so the simplest way that we can show this homolytic bond cleavage is by doing a reaction known as a pyrolysis. And so a pyrolysis really is just heating up a reaction until the bonds break. And so it's sometimes known as a thermolysis. Okay. All right, so a pyrolysis reaction increases the bond vibration amplitude so much so that the sigma bond is broken homolytically. So we can see this here with the molecule ethane. And so if we draw ethane in its Hawthorne structure, we can draw the bond dissociation energy, homolytic bond cleavage, by just heating this up. And so for ethane, what happens is you get homolytic bond cleavage. That sigma bond, those two electrons, get moved to each of the two carbon atoms. And so the net result is that you'll have two methyl radicals, which are not very stabilized, but you can see that this homolytic bond cleavage leads to these two radicals. And so for ethane, the BDE, right, is 90 kcals per mole. Now, this can only happen at really, really high temperatures, and not a lot of functional groups can survive these temperatures. And 90 kcals per mole is incredibly high to begin with. And so we must kind of resort to other methods of generating radicals. And so what we're really after here is trying to modify the system itself in order to generate a BDE that's much lower. And so, one way of doing that is actually to make a CC bond that's much weaker, right? That has a lower bond dissociation energy. One way of doing this is through cyclic structure, right? To introduce some strain into the alkane so that the sigma bond is broken more easily and releases some strain. So let's say we start with a cyclopropane ring, and we're going to heat it up, right? And so if we were to heat that cyclopropane up, we have a lot of strain energy associated with that molecule. And so the bond dissociation energy here is actually a lot lower. Right? And so you generate, instead of 2 radicals, you generate what's known as a 1,3 diradical. Right? But the bond dissociation energy here, the BDE, right, is only 65 kcals per mole. And so what we've done is we've taken a system and increased the strain of the cyclopropane ring to make it less stable and thus more likely to cleave homolytically. So that sigma CC bond is much weaker, and so you don't need quite as much energy to break that bond. Now, this is a somewhat limited strategy because not all synthetically useful starter materials have cyclopropane rings. So instead of trying to increase the energy of the starter material, what if instead we made the resulting radicals more stable? And so if the resulting radicals are formed via homolytic cleavage, if they're more stable, then the initial sigma carbon-carbon bond should be weaker. And so one way of illustrating this is with allylic systems. And so let's say we have 1-butene. And we're going to heat up 1-butene. And if we heat up 1-butene and we do a homolytic bond cleavage here, we would generate 2 radicals. One of those radicals would be a methyl radical, and the other radical would be an allylic radical. And so we generate a radical that looks like this, but that radical itself has another resonance form. And so what we've done is we've taken a system and broken it up into 2 radicals in which one of those 2 radicals is highly stabilized. All right? And so the bond dissociation energy here is not going to be quite as good as the cyclopropyl system, but it's much better than ethane. So this one is 76 kcals per mole. Okay, homolytic bond cleavage of that sigma CC bond generates a methyl radical, which isn't really stabilized, but the resonance stabilized allylic radical is really stabilized. And so the transition state energy is much lower, and this results in a lower bond dissociation energy. Now again, this is pretty limited, right? We've had systems where you have to increase the starter material energy by putting it into a highly strained ring, or having a system that generates these allyl radicals. Well, not every molecule that we might be interested in synthetically has these functional groups in them. And so another technique to generate radicals is to start with molecules that have especially weak bonds to begin with. Okay, so you may recall that the sigma oxygen-oxygen bond is very weak. And we have this from the reagent known as MCPBA, for example. Okay? And so sigma oxygen-oxygen bonds are very weak. And so we can take advantage of that because we can generate radicals very easily. So the bond dissociation energies are about 38 kcals per mole. And they can cleave to produce alkoxy radicals. And so when an acyl group is added to the peroxide, in an acyl peroxides, the bond dissociation energy is lowered even more to 29 kcals per mole. Okay, so we can see this in a variety of examples. So let's just do it. So this is an example of a peroxide, and so this peroxide can undergo a homolytic bond cleavage, and we know that when we do that, we generate 2 radicals. These 2 radicals are going to be oxygen-centered now, and so the bond dissociation energy here is about 38 kcals per mole. Okay. Now, what if we were to have a system that looks a little bit more like MCPBA, in which we're taking one of those alkoxy groups and we're placing an acyl group, C double bond O, on it. All right. If we heat that up this time, we can still get a homolytic bond cleavage, but this time we get one alkoxy radical plus a resonance stabilized radical. And so this bond dissociation energy should be lower. If this one was 38, this one is 29. Right, so the carboxy radical is resonance stabilized. We can draw another Lewis structure for that one. Okay. Now, this particular radical can actually undergo a cleavage itself. And so what can happen is you can get decomposition of that carboxy radical to give you CO2 plus an alkyl-based radical. So not only is the resulting carboxy radical resonance stabilized, but it can undergo release of a gas. And so this drives the reaction towards the products. Right? So that bond dissociation energy that we started with, that sigma oxygen-oxygen bond, is very, very weak. The other example are the azo compounds. And so azo compounds contain an internal nitrogen-nitrogen bond. And that's actually an internal nitrogen-nitrogen double bond. And what this might suggest is that you have a small molecule inside there that is highly, highly stable, the nitrogen gas. And so we can actually harness this for the generation of radicals. And so there's a compound known as AIBN, and I'll draw out the structure of AIBN here. All right, so this is AIBN. That stands for azo-bis isobutyronitrile. All right, this AIBN can undergo homolytic bond cleavage, but in the process you generate a molecule of nitrogen gas. And so follow along with the curly arrows. We're going to break this bond homolytically, and at the same time we're going to break this bond homolytically. And what happens is the two electrons in the middle pair up to give you a molecule of nitrogen gas, and then in the process you're going to generate two new carbon-based radicals here. Right, so the bond dissociation energy in this case, not quite as good as the acyl peroxides, but still quite good. This one is 31.9 kcals per mole. And so now that we know how to generate radicals in the first place, we need to kind of know what they do afterwards. Right. Once they're generated, there are several reaction pathways available to radicals. So let's talk about the radicals and their reactivity. All right. So these are classes of reactions. These aren't particular reactions, but there are ways that we can draw the curly arrows for radicals. The first type of reaction, type of mechanism that radicals undergo is something known as an abstraction. And so an abstraction is a process by which a radical species takes a hydrogen atom from another molecule. Right? So we say that it abstracts a hydrogen atom from another molecule. Now notice I said hydrogen atom. Right? So this is different than deprotonation. In a deprotonation, you are taking just the proton and not the electrons. In the case of radical abstraction, a radical species takes the hydrogen atom and the electron with it. And so an example of this it can be found below. So let's say we have this ethane molecule, and we react this ethane with a methyl radical, right? So we have somehow generated this methyl radical. That methyl radical can abstract a hydrogen atom from ethane, in this case, from another molecule. So how does it do that? Well, it is basically going to grab the hydrogen and the electron. The other electron moves up onto that carbon atom as an unpaired electron, so it generates another radical. And so the net result of that is that you get a molecule of methane plus an ethyl radical. Okay, so that's the first class of reactions that we have for radicals. Second class of reaction that we have for radical is known as a disproportionation. So this is a process by which a radical species abstracts a hydrogen from a vicinal, or in other words, adjacent, from an adjacent position of another radical. To produce an alkane. Or I should say an alkane and an alkene. Okay, so let's say we have a methyl radical, and then we have, in this case, an isopropyl, a propyl radical. These two radicals can come together and undergo a disproportionation reaction. And so this radical, this methyl radical is going to abstract the hydrogen that's sitting on the adjacent atom to the carbon bearing that ethyl radical. And so we're going to basically take and abstract that hydrogen. The other electron is going to move in to form a double bond with the other radical. And so the net result is that we get CH4, methane again, plus we get an alkene, propylene. And so this is a disproportionation reaction. Okay, the number 3 type of reaction that we have for radicals is known as a beta cleavage. And so in beta cleavage, this is a process by which a radical decomposes to give an alkene and a new radical. Okay, so let's say we have this butyl radical. This butyl radical can undergo a disproportionation reaction. So we're going to take, let's say, the radical and one electron from the CC bond next door, pair those up, but then the other electron moves up onto the other carbon atom as a radical. So the net result is that we have a methyl radical plus an alkene. Okay? And so this is a process by which the radical that we started with decomposes into an alkene, in this case propylene, plus a new radical, methyl radical. Right? So this is known as a beta cleavage. You can think of this as being the alpha bond, and this is the beta bond. Okay, the fourth type of reaction that we have is what's known as a dimerization. Okay, and as the name implies, this is a process by which two radicals react with each other. And they're reacting with each other directly right, to form a sigma bond. Okay, and so we can say this radical is reacting with this radical to give us a hexane. And we can couple those two electrons together. Right, so this is a dimerization reaction. And the last type of mechanism that we have, or reaction that we have for radicals, is known as an addition. So in an addition reaction, this is a process by which a radical either adds to a pi bond or cleaves a sigma bond, all right, to generate a new radical. Okay, so let's do the first case. So radical adds to a pi bond. So let's say we take this bromide radical, and we're going to take that bromide radical and add it to the pi bond. Right, so the bromide is going to add, in this case, those are going to couple up. Half of the pi bond makes a new sigma bond to the bromine, and the other comes up onto the carbon atom as a new radical. And so we have now this new carbon-bromine bond being formed. In the process, you generate a new radical species. In the second case, where you take a radical and it cleaves a sigma bond to generate a new radical, we can say, let's take a chloride radical, and we're going to add it to, let's say, methane to generate a new molecule of HCl plus methyl radical. Okay? And so these 5 classes of mechanisms, 5 classes of reactivity of radicals, we'll see these types of radical processes in 2 different types of reactions. One is the radical addition of alkenes, and the second is the free radical halogenation. And so stay tuned for those in the next lecture.